All right, so let's take a look now at how we can use equilibrium expressions and how we can manipulate them as well, in addition to a couple other things that we need to consider. So the first that we'll consider here is the fact that in the examples that we've looked at so far, okay, everything, the reactants and the products were in the same phase, meaning they were homogeneous equilibria. Equilibria. So all reactants and products were in the same phase, usually all aqueous or all gases. What happens if we have other physical states or phases present? Well, if that's the case, what we end up with is not homogeneous equilibria. Instead, what we end up with is heterogeneous equilibrium. And that's where the species in your reversible reaction are not all in the same phase. Now, if you have heterogeneous equilibrium, and you need to interpret or use that, one thing to keep in mind is that only your species that are in the gas phase and aqueous species, those are the only thing that appear in the equilibrium expressions. Okay, so when you write your Kc or your Qc expression, only gas things or only aqueous things appear in them. Pure solids and pure liquids do not. And the reason is the concentrations of solids don't change, and the concentration of liquids don't change either. They're constants, in other words. And as a result, we can not ignore them, but we don't need to incorporate them in our equilibrium expression and in our calculation as well. So for example, let's take a look at this one up here. So we have carbon dioxide reacting with carbon to produce carbon monoxide. So if I were to write a normal Kc expression for this, we'd have the CO, carbon monoxide, to the second power divided by CO2, okay, to the first power times C to the first power as well. What you will notice though is that the carbon is a solid, right? And that means that its concentration doesn't change. So this thing here in yellow, that's a constant, right? The concentration is not changing. So this is a constant. And what we can do is we can move this over to the other side where there's another constant, the Kc constant. So if I move that over, what I end up then with is Kc times C, concentration of C, is equal to CO2, I'm sorry, CO squared over CO2. Now I have a constant, Kc, times another constant. Guess what? That is going to give me now the product of two constants is a brand new constant. And that's equal to the CO squared divided by CO2. Right? And that's why we can use these expressions. We can simplify them when we're dealing with heterogeneous equilibria. We don't need to include the solids. Same thing applies to the liquids. The concentration of a solid doesn't change. It's a constant. Concentration of a liquid doesn't change. It's also a constant. So for instance, if you look at the second example down here, where we have a solid, we have a liquid, we have a solid. So these are not going to appear in the equilibrium expression. The only thing that would be present would be your H2 to the second power, because that's the coefficient, right? So it simplifies for that particular equation, Kc equals H2 squared. So you want to pay close attention to the physical states, right? The things that are in parentheses, solid, liquid, gases, or AQ, those are going to be very important when you write your Kc expressions. And as a result, when you evaluate the value for Kc, they will come into play as well. The next thing we can do with our equilibrium expressions is we will be able to manipulate them. And this is going to look slightly or very familiar to you, especially, I'm just going to say recall up here. Back in the thermochemistry section of Gen Chem 1, okay, where we looked at Hess's law, and we saw that we could manipulate thermochemical equations. And specifically here, we're looking at things like your delta H values, your enthalpy values, etc. We're going to see something very, very similar in terms of how we manipulate equations, our equilibrium expressions to be more specific in our equilibrium equations, but what we actually do with those Kc values. Now, it's going to be similar, but there are going to be some big differences in terms of how we deal with the Kc values. All right. So let's take a look at some examples of these that we have up here. So your book does a really good job of just making up some expressions and some values and then showing you what the manipulation is and how that affects the equilibrium expression, but how it also affects the value relative to the original Kc value. So we have here an equation between A and B to produce C. And then the Kc value for this is given as whatever that number is. And we have another expression, C, turning into D and E, and we have a Kc value for that one as well. All right, so what this is saying now is each of these options down here, we're going to do something to these original equations, and then we're going to see what it does to the equilibrium expression and also what it does to the value for Kc. So here we have carbon breaking down or turning into A and B. That is just the reverse of that original equation. So if you were to write the expression for this reversed equation, right, it'll be the products over the reactants, right? And if you compare it to this original equation here, if I were to write that Kc expression, right, it's C squared over A times B. Well, what's the relationship between this expression here and this one? Well, they are inverse to each other, right? It's one is one over the other one. So as a result, the value for the Kc is also the reciprocal or the inverse of the original equation, right? So when you reverse an equilibrium expression, whoops, what you do is you take the reciprocal of the Kc value. Okay, that's the first thing. If we were to multiply an original equation by a certain factor, so for example, if I take this equation here and I multiply it by 2, okay, I change my coefficients now to 2, 2, and then 4, right? That's what I have here. So the original equation is multiplied by 2. How does that affect the equilibrium expressions? So now it becomes C to the 4th power times A to the 2nd and B to the 2nd. Well, how does this related to this expression here? Well, this is all of this to the 2nd power, right? So when you multiply your original equation, what we do to the Kc value is we raise it to whatever that number is. It's raised to the to that same number. It's right. We squared everything, multiplied. I'm sorry. We multiplied this original equation by 2. That means we're going to square everything. We're going to square the Kc value. What about if we divided an original equation by a certain number, right? So if we take a look now at this equation here, right, this is related to this one by dividing that original one by 2. Okay, so if I divide everything by 2 now, my coefficients get divided by 2, right? The 2 gets divided by 2, this becomes a half, and then this becomes a half. So then this here turns into 1. So when I have my new equation now and I write the Kc expression for that, what I end up with, right, is this as my expression. And what we do when we divide that original equation by 2, we end up taking the square root of that original equation, right? So it's the square root of that initial thing. So if I take my original equation up here, in order to get to this to become that equation, we actually have to take the square root of this entire thing. So that means we need to take the square root of the Kc value as well. And the last possibility here is if I were to add two equations together. So if I were to add equation one, the first one and the second one, right? But if I add these two together, just according to normal adding equations together, these two are going to cancel out. So I end up with A plus B producing C and D. Okay, so we add those two equations together. Then when I write the Kc expression for this, right, I have my D times E divided by A times B. How is this now related to that original equation? Well, now I actually have two of those things to consider, because I have the Kc expression for that equation. I also have my Kc expression for the second one. So this then would be Kc for that. Kc2 in this case would be equal to, what do we have? D times E over C, and then that's squared, right? So how are these two expressions related to that expression for that when we add them together? Well, you can maybe see if I take these two and I multiply them times each other. Let me get rid of the square root sign. So if I take these two and I multiply them, okay, so now I'm going to have C squared over A times B, and I'm going to times that by D times E over C squared, right? The C squared cancels out. I end up with D times E over A times B. Guess what? That is exactly what I can write here for my expression when I add those two together. So that Kc then is just the product of those two equations that I added together. So just multiply those values to end up with the new Kc value for the sum of, in this case, those two equations that I added together. So there are some similarities between what we're doing here and what we did in Hess's law on thermochemistry way back when, but there's some big differences in terms of what happens to the actual Kc values. When we reverse an equation, when we multiply by a certain number, when we divide it by a certain number, or when we add equations together. Okay, so when we have a situation where our equilibrium expression contains only gases, we can write another form or a different form of the equilibrium expression, which accounts for the species present, not in terms of the concentrations of the gases, but instead in terms of their partial pressures. And that's going to be usually in atmospheres. So for instance, we've seen previously that if we have this equation here, N2O4 producing NO2, we can write the Kc expression for this, right? It's the product, NO2 squared over N2O4 to the first power, right? That's our normal expression. What we're saying is now, because all of the species are gases, and this is the only time we can do this, if all of the species in our equilibrium expression are gases, we can write what's known as a Kp expression, right? So the P now here, meaning partial pressure as opposed to concentrations, where the C represents, and that's molar concentration. So that we equal now to the partial pressure of the product, in this case, NO2, again now, squared, divided by the partial pressure of the reactant, N2O4, to the first power. Okay, now the relationship between Kc and Kp, okay, because concentrations are not necessarily equal to partial pressures. You can't assume that they are. So there's a relationship between them. So we can say then that the Kp, we won't go through the derivation of this, but it's not that difficult to derive the expression. Your book does a good job of walking you through that. The Kp expression is equal to the Kc expression in terms of concentration times the gas constant R times the temperature, the thermodynamic temperature in Kelvin. Let me actually put this in regular parentheses so we don't get it confused with concentrations. And then that's raised to the power of the change in the number of moles of gas, right? That is the relationship. So the delta N here, and that's a triangle, meaning the change in number of moles of gas. And again, to get the change in anything, it's the number of moles of gas in the products, because the ending point here is our product, minus the number of moles, total number of moles of gas reactants. Okay, and in this particular expression here, your R value, that's the gas constant, and the unit that we're using, or the value that we're using, is 0.0821 liter atmosphere per mole Kelvin. Okay, and then your temperature here is in kelvins. Okay, so you need to convert it. If it's in Celsius, we add 273 to it to get it to the Kelvin temperature. So in the example that we looked at up here, in this one, okay, so the number of moles of gas that I have in the product, I have 2 moles of gas. And my reactant here, I have 1 mole of gas. So the change in the moles, delta N, would be the product number of moles 2 minus the reactant number of moles, which is 1. So delta N there is actually 1. Right? And that's how you calculate that. You add together the total number of moles from the balanced equation, total number of moles of gas on the product side, minus the total number of moles of gas on the reactant side. And that gives us our delta N. And we just substitute that into our equation. If we know what Kc is, we know R is a constant, we can solve for the Kp value as well.